Hello students, I welcome you in today's session of physics, and in physics I am going to take your chapter number 16, which is your surface tension. Clear? So this is your first lecture, and you can see first just have a look what is the syllabus and what you have to study. So first you have to see that surface tension, molecular theory, drops and bubbles, angle of contact, work done in stretching a surface, and surface energy, capillary rise, measurement of surface tension by capillary rise method, excess pressure across a curved surface, application of surface tension for drop and bubbles. So these are the things you have to study in this chapter, and we will cover out in our lectures. So in today's lecture we are starting with the first topic, which is our surface tension. So what is the surface tension? You can see here the free surfaces of a liquid which is surface in contact with air are in the state of tension and behave just like a stretched membrane. Fine. So qualitatively, surface tension is a liquid is the property by virtue of which the free surface of the liquid behave as a stretched membrane and has the tendency to acquire the minimum possible area. Means every liquid try to minimize its surface area. Clear? So this is the property called surface tension. This is from the figure you can see here. There is however a difference between the tension in a liquid surface and that in the membrane. So the tension in a stretched membrane increases as the stretching increases, whereas the tension in a liquid surface remains constant. Now the quantitative definition of the surface tension, the second one we are talking here. Let us an imaginary, this is a figure, you can see that imaginary line AB, clear, can be drawn in any direction in a liquid surface. Here you can see that we draw a line on the liquid surface. So the surface on either side of it line exerts a pulling force on the surface on the other side. You can see here from the figure two equal and opposite forces are acting over this line. Fine. So this force lies in the plane on the surface and is at right angle to the line AB. So the magnitude of this force per unit length of AB is taken as a measure of the surface tension of the liquid. Thus, if F be the total force acting on either sides of the line AB of length is small l, then the surface tension is given by, I told you, the force per unit length. So this is the tension is equals to force by length. In place of length, if we take 1 meter, so tension is equals to how much? The total force. So hence, the surface tension of a liquid is defined as the force per unit length in the plane of the liquid. So surface acting at right angle on either sides of an imaginary line drawn in that surface. The SI unit is Newton per meter and its dimension is mt t minus 2. Now what are the factors which are affecting the surface tension? So here you can see there are the few factors which are affecting the surface tension, and what are they? Kindly read it. The first one, the decrease with increase in the liquid temperature and becomes zero at critical temperature. Second one is affected by the presence of impurity. If the impurity is highly soluble, for example the sodium chloride in water, then the surface tension of the liquid increases. But if the impurity is sparingly soluble, for example like phenol in water, then the surface tension of liquid decreases. So you can remember this, in what cases the surface tension increases and in what cases surface tension is decreases. Now come to the third one. It depends upon the medium present on the other side of the liquid. The fourth one depends only upon the nature of the liquid and is independent of the area of free surfaces. Clear? Come to the second one. This is the example of surface tension. The second one you are seeing, you can see here. These are the few examples we are taking here out. So the first one, if we tie a closed loop of a cotton thread between the 2 points of a wire frame and dip in a soap solution. So what happened? A thin film of soap solution is formed on the frame and the loop of a thread is placed the film in an irregular manner. So figure 2a, this is the 2a. If now the film inside the loop is broken by a needle, then what happened? The thread immediately assumes a circular loop. It means if you pierce this film with a pin, then what happened? It looks like the force is equal and opposite is in all same in all the directions. So that's why the shape seems like to be circular. You can see here. So the film outside the loop contact, thus the pulling the thread into a circle. So we know that for a given parameter, the circle has the largest area. This means that the film outside the loop contract to a smaller area. Clear? Now the second one, liquid bubble and drop are spherical because surface area of a sphere for a given volume is minimum amongst all shapes. The third one, the ends of a glass tube become rounded on heating. When the glass is heated, it melts to a liquid. The surface of this liquid tend to have a minimum area. So we know that for a given volume, the area of the surface of the sphere is minimum. Hence, the melted glass tends to assume a spherical shape. This is why the ends of the glass tube become rounded on heating. So this is the most important one. Small drops of mercury are spherical while large ones are flat. Why? So when a drop of a liquid is poured on a glass plate, the shape of the drop is governed by the two forces. Now what are the forces? The forces of surface tension and the forces of the gravity. So the drop acquires a shape in which its potential energy is minimum. So if only surface tension are acting, the potential energy would be minimum when the surface area of the drop is minimum. And so the drop would become spherical. You can see from this figure. On the other hand, if the gravity alone were acting, then its potential energy would be minimum when its center of gravity is at the lowest point position. In this case, the drop would spread out. Fine. So for every small drop, the potential energy due to gravity is insignificant compared to that of the due to the surface tension. So hence the shape of the drop is determined by the surface tension and becomes spherical. You can see from this figure number 3. For moderately large drops, the gravity play an important appreciable role and the drop are bit flattened. So for every large drop, the potential energy due to the gravity has the predominant influence. Hence the drop is spread out flat. So this is the important one. Now I am coming to this one. The flotation of the needle over on a water. So if we place a thin needle on a piece of a blotting paper and put the paper gently on the surface of water, so what happens? The blotting paper will soon sink to the bottom while the needle will remain floating on the surface. This happens due to the surface tension of water. From the figure 4 you can see this. This is the figure 4. Figure 4 shown the transverse section of the needle floating on the surface of water. So the two forces act upon the needle. The first one is the surface tension T, and the second one the weight of the needle on the resolving the tension forces. So you can see here the weight is acting downward and the tension is in this direction. So tension in the horizontal and the vertical component. Horizontal component cancel out each other and the vertical component are added, which balances the weight of the thin needle. So hence the needle floats. If however we add soap powder or oil in water, the needle sinks. So the reason is that the soap or oil lowers the surface tension of water, with the result that the weight of the needle exceeds the force of surface tension acting vertically upward. Clear? You can see here insects and mosquitoes swim on the surface of water in ponds and lakes due to the surface tension. So if the kerosene oil is spread on the water surface, the surface tension of water is lower and the insects and mosquitoes sink in water and are dead. Now I am skipping this. These are the few examples. I am coming to the intermolecular forces. Here you can see this is the important one, cohesive and adhesive forces. According to the molecular theory, matter is made of a minute particle which is called molecules, which can remain in a free state and attract each other. So the force of attraction between the molecules of the same substance is called cohesive force. Means the force which exists between the same type of bodies is called as cohesive force, and that between the molecules of different substances is called adhesive force. And if this force exists between the different bodies, then it is called as adhesive force. So these forces are different from the gravitational forces and do not obey the inverse square law. Clear? So if the distance between the molecule is greater than 10 to the power minus 9 meter, so the force of attraction between them is negligible. But within this limit, the force increases very rapidly as the distance between the molecule decreases. So the maximum distance is how much? 10 to the power minus 9 meter, up to which the two molecules attract each other and is called as molecular range. It is usually denoted by small c. It is not the speed of light, but it is the molecular range. The effect of cohesive and the adhesive forces are observed in daily life. It is due to the cohesive force that two drops of a liquid, when brought in mutual contact, coalesce into one. So it is difficult to separate two sticky plates of well glass fitted with water because quite a large force has to be applied against the cohesive forces between the molecules of water. Clear? The definite shape of solid substances is also due to the cohesive forces present between its molecules. Now what is adhesive forces come into play when two different substances are brought in contact. So when we pour water on a glass plate, the plates become wet because the molecule of water stick to the molecules of glass under adhesive force. So in order to dry the wet plate, it should be wiped by a substance whose adhesion of water molecule is greater than that of the glass. Clear? This is the important one. Why the water wets the glass surface but mercury does not? So the adhesive force between the water molecules and the glass molecule is greater than the cohesive force between the molecules of the water. So hence when water is poured on a glass, the water molecules cling to the glass molecule and the glass surface is wetted. This is the reason. On the other hand, the adhesive force between the mercury molecule and the glass molecule is less than the cohesive force between the mercury molecule. Hence mercury molecule do not cling with the glass molecules. Fine? That is, mercury does not wet the glass. If however the glass surface is greasy, then the water does not wet the glass because the adhesive force between the water and the glass is less than the cohesive force between the water molecule and themselves. The adhesive force between the oil and water is less than the cohesive force of water but greater than the cohesive force of oil. Therefore, a water drop poured on the surface of the oil contract to take the form of a globule, while a drop of oil poured on the surface of water is spread to a large area in the form of a thin film. So the adhesive force between a ink and a paper is greater than the cohesive force of a ink. That is why ink sticks in paper. Writing on a blackboard or by chalk is also possible due to its adhesive force. I hope you understand it. Now here is the explanation given of the surface tension on the basis of intermolecular cohesive forces. So come to fourth one. This is the explanation we are going to discuss about. Laplace explained the phenomena of surface tension on the basis of intermolecular forces. Clear? So we know that if the distance between the two molecules is less than the molecular range, which is your 10 to the power minus 9 meter, I already told you in the above topic, then they attract each other. But if the distance is more than this, then the attraction becomes negligible. Clear? Therefore, if we draw the sphere of radius molecular range with a molecule as a center, then only those molecules which are enclosed within the sphere can attract or be attracted by the molecules at the center of the sphere. This is called the sphere of molecular activity. Now there is an activity given here. You can see from this figure, this one, liquid surface area. So what you have to do, you have to read this theory and tell me what you understand from this theory, because I am skipping this and I ask you in our next lecture what you learn from this. Now I am coming to the shape of liquid meniscus in a glass tube. I hope you know what is meniscus. The concave shape, if we pour a water in a tube, the concave shape water takes a form of concave shape, that is called as the meniscus. So when a liquid is brought in contact with the solid surface, the surface of the liquid becomes curved near the place of contact. Clear? So the nature of the curvature, concave or convex, depends upon the relative magnitudes of the cohesive force between the liquid molecule and the adhesive force between the molecule of liquid and those of the solids. So here you can see these are the two figures given in here. Figure number A, water is shown to be in contact with the walls of the glass tube. Clear? So let us consider a molecule A on the water surface near the glass. This molecule is acted upon by the two forces of attraction. The first one is the resultant adhesive force, which is P, which is act on A due to the attraction of the glass molecule near A, and its direction is perpendicular to the surface of the glass. Now what is the second? The second one, the resultant cohesive force which acts on A due to the attraction of neighboring water molecule is acts towards the interior of the water. Here you can see. Now the attraction forces between the water molecule and the glass molecule is greater than the cohesive force between the molecules of water. Hence the force P is greater than the force Q. So their resultant R will be directed towards water. From the figure 6a you can easily understood it. This is the resultant. Now come to the figure number 6b. In the above figure, this is the 6b. Mercury is shown to be in contact with the walls of the glass tube, so the cohesive force between the molecules of the mercury is far greater than the adhesive force between the mercury molecules and the glass molecules. Hence, in this case, the force Q will be much greater than the force P, and their resultant R will be directed towards the interior of the mercury. Their resultants are X on all the molecules on the surface of water or mercury. You can see here these figures. So for the molecule more and more away from the walls, the adhesive force P goes on decreasing, while the cohesive force Q becomes more and more vertical. So consequences, the resultant R become more and more vertical. So in the middle of the surface, P becomes 0 and Q become vertical. So hence the resultant R become exactly vertical. So if the surface of the liquid is in equilibrium, the resultant force acting on any molecule in the surface must be perpendicular to the surface. So hence the liquid surface sets itself perpendicular to the resultant force everywhere. That is why water surface assume a concave shape, while the mercury shapes assume a convex shape. This is the reason why the mercury assumes a convex shape and the water assumes a concave shape. Clear? So in either case, the resultant force in the middle is vertical and the surface is horizontal. You can see here from this figure A and B. This is 7. This is the important one, the angle of contact. Clear? What is the angle of contact? So the angle inside the liquid between the tangent of the solid surface and the tangent to the liquid surface at the point of contact is called as angle of contact for the pair of solid and liquid. Here you can see the note given here. So the first one, the angle of contact for those liquids which wet the solid is acute. It is 0 for pure water and clean glass. For ordinary water at glass it is about 8 degree. This is the most important one. So please note down it. What is the angle of contact for the pure clean glass? For ordinary water and glass it is about 8 degree, and those liquids which wet the solid, the angle is acute and is 0 for pure water. From these figures you can see this. Now what is the second one? The liquid which do not wet the solids have obtuse angle in contact. Just say for mercury and glass the angle of contact is how much? 135 degree. Come to the third one, the angle of contact for water and silver is 90 degree. So hence in a silver vessel the surface of water at the edges also remains horizontal. Clear? So this is the end of the lecture number 1. We will discuss about the topic number 7, which is work done in stretching a liquid surface energy of a liquid, in our next lecture, which is lecture number 2. Clear? So from this I am ending this session. Thank you class. Thank you very much.